Hello and welcome back to differential equations. After technical difficulties, let's see if this thing actually works over here. And if we are live, we are going to talk about power series. Let's see. Come on, YouTube, you can do it. Let's see. All right. I think this is working. So, yep. Let's see how it goes. Perfect. Yes, thank you. Thank you for confirming, and now let's go and talk about power series. Today's lecture is technically a repeat of what you learned in Calculus 2, Chapter 11. Some of you had it last semester, some of you had it a year ago or so. So we have to go through these basic things which are supposed to be everyone's, playing field. And then the next section 8.2 will solve differential equations. So no differential equations solving today. We are only working on the review, and we are learning about derivatives and shifting the counter for our power series. So first of all, let's go and look at the definition of power series. We had the definition that f of x is equal to some kind of, oops, I forgot the sum, bad sign. So 0 to infinity of Cn and then x to the n, right? So this is the basic, this is it. Now, this is, now I see some question. No, the exam ends at noon tomorrow. Oh my God, people read. So we have the power series, and now this one is centered at 0. This one is centered at 0. If I put summation 0 to infinity Cn x minus a to the n, this one is centered at a. And we need to have this, right? We need to have this one because calculations might not be close to 0. What if you have to calculate at 1? What if you have to calculate at 10, right? So we need to be able to shift the approximation left and right to accommodate the calculation for the point that we are interested in. Now, the power series are obviously the most powerful way to solve the problem. And obviously it's going to be one of the messiest way to solve the problem. And in order for us to do this, just like Laplace transform, where you use Laplace to transform all of the functions into Laplace, right, domain, over here you will transform all of the functions into power series, because there is this correspondence between the power series and the function. And then you would work on power series to solve the problem, and then we are going to go and unwrap it, right, from power series back into function domain, and you will have your answer. So these are basic definitions, and we learned only a particular power series called Taylor series. So now this is called scratching the surface in education, right? Because your Calculus 2 provided you only with the Taylor series, which are the polynomial approximations. There are Lorentz series, Fourier series. There are a whole bunch of series that are out there in the world. And we are going to take a look at the basic Taylor series, where these coefficients Cn are all just given by the formula that computes from the derivative and from the factorial. So for Taylor series, our f of x is still, right, the basic definition Cn x to the n. That's the basic definition and the form for the power series. But this Cn, right, is given by the nth derivative computed at a divided by n factorial. Oh, I forgot the sum again. I'm completely disshuffled because of the issues I had. I had to figure out what's going on. So there we go. Nth derivative at a divided by n factorial times x to the n, or x minus a to the n, depending on, right, where is your center. So this is the power series, right, that we are focusing on today. Well, in this chapter, again, this is basic introductory course of differential equations. You know, you can spend years learning. As I mentioned, we are only covering a fraction of 1% of what's there with this whole course. We have, you know, we are truly doing just the most basic and elementary things in mathematics in this course. There is a lot more to be added to this. Let me check the chat again. I hope this was a troll question. If the exam ends at midnight, because exam clearly said in the announcement that it ends at noon. So, and I'm using the word noon, so there are no issues with that. I am. The exam should be closing at 11:59 a.m. tomorrow, right, on Tuesday. Let me get my cheat sheet just to check. So differential equations 5, which is tomorrow, Tuesday at noon. Okay, great. Yes, so it closes at noon, so you have all day today and then tomorrow morning if you want to take the test. Now I gotta interrupt this lecture. Next one, what was Cn? Well, I explained. Cn is this Cn is the coefficient for each of the powers. I'll write it down. And then I can't hear you. All right, so is sound the problem? Because my software is showing that the sound is being pushed out. I guess that would be issue on your end. I'm not getting anyone else saying I can't hear you. Okay, there is a confirmation that sound is working. So try the headphones or maybe change the adapter if you are using multiple sound cards. Try changing the adapter to a different adapter to see. Okay, perfect. Yay. Thank you, guys. And good. All right, so the chat caught up. Everything is in order. Let's talk more about coefficients now. So we all know so far that this is the definition for not powers, the derivatives of the function. So if I want to write out my power series, it will be f of x is equal to, and we will have the C0 f0, that's a zeroth derivative at a, times x to the 0, or divided by 0 factorial as well, plus, I don't need C0, I'm writing the coefficients down. Then the first derivative, we can just put the prime, divided by 1 factorial, x to the 1, plus second derivative computed at a, 2 factorial x squared plus, this is number 1. I have to use the proper way of writing number 1, and that's a prime on the f. F triple prime computed at a divided by 3 factorial, then x cubed plus f to the, and this is where the notation switches to the 4 factorial, there we go, x to the 4 plus, and I'll just put dot dot dot. I will put the nth derivative, but that's not the end because it will go forever. And now when you just write this in a basic form, the zeroth derivative of a function is the function itself. So the whole, and the 0 factorial is defined as 1. So those two basic ideas. So zeroth derivative of a function is just a function, and 0 factorial is defined as 1. So those are some basics from before. So we have the first term just to be f of a plus, and then we have f prime of a, divided by 1 because it's a 1 factorial, that's 1. That's f of a x, and then plus the second derivative computed at a divided by 2 x squared plus the triple derivative computed at a divided by 3 factorial x cubed plus, and that will go on forever. So all of the coefficients, what we call the Cn, right, are given by the nth derivative computed at the value you are approximating at n factorial. So this is again something that was there in Calc 2. I believe they give this both in 11.1 and 11.3 with the current textbook that we are using. Now, the power series that you should know, just to write out, by heart, like you know what the derivative is for x squared, you know what the integral is for x squared, integral and derivative for e to the x and ln x and all that kind of stuff, right? You learned a whole bunch of these things. Knowing these 5 power series would help you greatly in computing these things. Again, we are only doing the very introductory idea here, very basic ones, and these are the ones that you will be using in the future courses, which utilize differential equations and power series to solve it. So I'm talking about 300 or 400 level courses when you transfer out. So these are the absolute basics. So one of them is going to be 1 over 1 minus x, which can simply be written as x to the n from 0 to infinity. And when you write out the power series for it in terms of the terms, you just get this basic like this. And if you ever get your answer when you solve differential equation to look like this, then that can be compressed into that, and that's that. Now, to obtain this, right, if you want to compute this, again, I'm talking about memorizing one of the basic power series. You are memorizing that this equals to that, right, with this being intermediate step. So having this power series here, the way you would compute it is just a regular way, right? You will be expanding it because these are all x's, then your a is 0. So you are just computing the derivatives of this and plug in x equals 0 to calculate all of these. And then when you multiply by everything, you will see that they cancel the coefficient, the factorials and so on, so you will just get this string. Now, the other one that you actually rarely need is the one that has a plus in the denominator. and that one will introduce negative 1 to the n, x to the n. So see, the second one is a joke to remember if you know the first one, because all it does is it introduces this term here, and this becomes now 1 minus x plus x squared minus x cubed plus x to the fourth minus x to the 5 plus dot dot dot, right, going on forever. So it's very simple to memorize the second one when you know the first one. Now these are the ones that are obviously the top one is the one that shows up as your solution, I would say, frequently. But the one that the ones that are actually showing up very, very frequently are obviously e to the x, and that one is given by x to the n over n factorial. Now, if you just write out these terms, it is 1 plus x squared over 2 plus x cubed over 6 plus x to the fourth over 24 plus dot 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 going forever. So that's another basic one. So again, this one is not basic. You don't generally write, but it's easy to remember it because of the one on the top that you should know. So these are the ones that you should know by now. Another two are sine and cosine. And for me as a student, these were especially easy to remember and memorize because I knew the rules from pre-calculus when I learned trig for the first time. And when I saw power series for the first time, I was amazed because I learned things that I didn't know before. They were just, served for me to memorize. And then when I saw the power series, a lot of stuff started making sense. If you take a look at the sine, right, it will have negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial from 0 to infinity. And when you look at the power series, right, you get, I'll put the factorials even though, I can put a 6, whatever. We see it's, this is 5, then that's 120, and then x to the 7 over whatever 7 factorial is, plus dot dot dot. This one was so easy to memorize because what is the 2n plus 1? That's for odd numbers. And we know that the sine function is odd function. And why? Well, all of the powers are odd, right? It's odd function, and it satisfies that condition for odd functions that you learn in pre-calc 1. You learn the condition, and then in pre-calc 2, when you learn trig for the first time, they ask you to memorize that sine function is odd. No explanations given at all. Why? It's because it is. It's because it is odd, right? And cosine was even because it was even, and that was it, right? It was just defined in a little box, and you were supposed to memorize that. And I never liked it, right? Because it's just, I don't like to memorize stuff that is not connected to anything else. Right, so it bothered me when I was in trig course. But then when we completed the calc 2 and I seen the power series and I saw that all of the sines have the odd exponents and then all of the cosines have only even exponents, well, now even and odd make a lot of sense. Right? So now you have 2n is even, and this one is 1 minus x squared over 4 plus x to the 4 over 24 minus x to the 6 over 6 times this 720 plus, right, dot dot dot. So when you take a look at the sine and cosine ones, holy nightmare that works well, right? Because it gives you all the even powers, and we know cosine is even function, so it's a joke to remember it. Now, a lot of your functions will end up being hyperbolic answers. And hyperbolic functions are so easy to memorize because if you know these, then all you need to do is to remove these alternating terms and you will get your hyperbolics. So sine hyperbolic x is the power series of x 2n plus 1 over 2n plus 1 factorial. So you just take out the alternation. And the power series is just x plus x cubed over 6 plus x to the 5 over 120 plus x to the 7 over whatever the hell 7 factorial is plus dot dot dot. And cosine hyperbolic x is the same as cosine x without alternation. So we just have x to the 2n divided by 2n factorial, and that gives us 1 plus x squared over 4. Why did I say x squared over 4? It's x squared over 2. It's a 2 factorial. And 2 times 1 is 2. Holy nightmare. And then we go plus x to the 4 over 24 plus x to the 6 over 720 plus dot dot dot. So when you have alternation in signs, right, you go plus minus plus minus plus minus. When you have that negative 1 to the n term, those are sines and cosines. And if you have just pluses all around, those are the hyperbolics. So they're very, 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 very easy. And I will just say, usually, again, we are only in introductory course. All of these are the basic ones that would show up as answers, and you just need to recognize the pattern and then plug it in. Now, your textbook also lists one of the basic LNs. I haven't seen problems generally that have it. I'll list it here, for completion, I guess. And I don't know, if it shows up, you'll hopefully recognize it, but generally I haven't seen it used, but then maybe I haven't done enough problems. I don't know. Well, here, let's write x to the 4 over 4 plus dot dot dot, whatever. So these are the basic power series. Now, what happens if you need something composite? What happens if you need to find, let's say, cosine of x cubed? So another theorem which you supposed to know from 11.2 is that the function composition is allowed inside power series. So the way to deal with the cosine cubed is you write the cosine definition down, and that is going to be by what we had up there. It's going to be 1 minus x squared over 2 plus x to the 4 over 24 minus x to the 6 over 720 plus dot dot dot. And then if you have cosine of x cubed, you will replace every x with x cubed. So you are going to have x cubed squared over 2 plus x cubed to the 4th over 24 minus x cubed to the 6 over 720. And then you just work out that algebra, right? Power of a power is x to the 6 over 2 plus x to the 12 over 24 minus x to the 18 over 720 plus dot dot dot, and that's going to go forever. And that would be idea for how to get cosine cubed. And now that goes for everything else. If you want to have, e to the x to the 7, you want to have e to the, sine x, you can put a power series within power series, then they're nested. It's a lot of things that you can do with this. Now, obviously, when you start nesting power series, that's going to be a graduate level course called asymptotics. But again, there is a lot more to learn than the bare minimum basics that we are covering in this course. This is just introduction to differential equations. That's all we're doing here. All right, cool. So hopefully by now we understand that there is this creature called power series which turns functions, like you see them here, turns these functions into polynomials. You have polynomials on the right, and polynomials are easy to differentiate, they're easy to integrate, they're, to manipulate. So everything is easy with polynomials except finding roots. They're absolute nightmare to find roots. But other than finding, roots, finding zeros, or x-intercepts, whatever you want to call them, other than that, polynomials are awesome for everything else. And then, especially this theorem here that helps us work on a function composition, right? To come up with a composite function from the basic ones that we memorize, is a really a good feature, because we could have function composition inside our problems. Now, some of the basic properties of power series would be that addition and what we call linearity, right? So multiplying by a coefficient, constant coefficient, d, let's say, and adding and subtracting power series. Those are some of the basic properties. So basic properties. If you have a power series such as, let's say, some constant d times Cn x to the n, then that d can be kicked outside. Because please note that I'm going to put this in air quotation marks. The variable for this power series is n. The summation is ordered through n. So any constant or any variable like x that contains n, the power series, the summation will operate on it. D did not have any of that, so it can be kicked outside. So let's say, let me just box this one. So let's say that you have a power series which says 2 n minus 1 x to the n plus 7, right? You have something like this. Then you can kick these two outside, and you just have your n minus 1 x to the n plus 7 stays inside, because you need to be able to use the n's, because this n starts at 0 and then goes 1, 2, 3, 4 to create all of the terms for this mess, right? These two would be multiplying every single term, because you'll calculate the first term using n equals 0, second term you calculate when n is 1, third term when n is 2, and so on. And every single one will be multiplied by 2. Now, you can factor all of those 2's out, right? Because if you have infinitely many terms and each one of them is multiplied by 2, because as you can see here, each term is multiplied by 2, well, factor that 2 out, right? So that's what our first rule is. If your power series is multiplied by a constant, you can kick that constant outside. Now, hint, hint, hint. Second order constant coefficients, right? Second order constant coefficients equations, which we covered in chapter 2 and we covered in chapter 3, and then we had the systems of them in chapters 4 and 5, right? We had a lot of constant coefficient differential equations. So if every single one of those terms, the second derivative, first derivative, and the function, right? Because you had y double prime, y prime, and y, all of them will have some constant in front. That's 3 power series in there that we need to combine. Those constant coefficients in front of y double prime, y prime, and y would be the ones that you would kick in front of the series, like you see it here. You can, I mean. The problem will dictate if you should or not, but you can. Another one that actually builds our differential equations is ability to add and subtract, right? So to either combine or split apart summations. So if you have a summation of Cn x to the n plus minus dn x to the n, this is also written as summation 0 to infinity of Cn. Well, actually, I should write it here. Summation, and then the conclusion we can put down there. Cn plus or minus dn times x to the n. So this is the same. All of that could be when you split these power series apart, because we are only dealing with sums here. So you can split series apart, or you can put them together. Now, you have to be extremely careful here. You have to have the same x to the n. You have to have the same start for your series. So I'm going to do this, and I'm going to say a to infinity. I need an O there. Both series must start with the same number, which is the counter. That's the counter. It starts at 1, or it starts at 2, or it starts at 7, but that's the one that goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right, which creates all of the terms. So in order for the theorem in blue to work, they both have to start at the same number. Now I have zeros across the board, but they could all be 1s, or they could all be 2s. If they are not starting at the same value, you have to shift the counter. And this is where the pain of this course begins. Because as soon as you will see today, as soon as you take the derivative of the power series, the counter shifts and it doesn't match the original function, and you have to do shifting the counter. So if the numbers do not match, we must shift the counter. Now, shifting the counter is a skill which you learned in chapter 10 in Calc 2 when you shifted the counter for geometric series to make it start at 0, so you can use the sum formula to calculate the sum of geometric series. So that's the first and only time when you learned shifting the counter. Now you will be using shifting the counter in every single problem, sometimes even multiple times. So that's number 1. And number 2, power on x to the n must be the same. That's another feature that you have to have in order to combine two power series that are not working together. Now, being that we are reviewing these basic ideas today, I'm going to actually review that now, because without this you just can't do anything. So I'm going to repeat the problem from Calc 2 the way you learned it the first time, because our calculations here will have more terms to consider. So let's just review the basic example, what I would say, the baby steps, right? So say that the power series given to you started at 2 instead of the 0, and you were supposed to calculate 3 over 4 to the n. So this is your converge or diverge problem from Calc 2. And if converge, what's the sum? So, you know, something like this would be a standard calculus 2 final exam, right? Question. It is a question that you are supposed to do quickly, right? Because your power series for geometric series has to start at 0, go to infinity, a r to the n. It converges if r is smaller than 1. Well, if r is between -1 and 1. And it diverges if r is bigger or equal than 1 or smaller or equal than -1. This is the easy way to write anything else. Now, if it's convergent, you can calculate the sum as a over 1 minus r. So this problem, if this is a 0, is a joke. You look at r, in our case 1/4, that's smaller than 1, and it's convergent. There are no calculations here. You just look at r. Now this 3 is technically, if you use basic algebra, this is like that, right? When you rewrite it. So the 3 jumps down because exponent is only on a 4. Then the 1 stays up because 3 jumped out. And you just have 1 over 4 to the n. And your r is 1 over 4, and that's less than 1, and that converges. So that should take less than, 5 seconds. Just how long it takes you to write this. That's it. Now, the issue is, if it converges, what's the sum? We have to use the formula. Now, if you are any good in reading formulas, you are careful to see that the formula for the sum will work only if that's a 0. In our case, it's not. So we have to use what we call shifting the counter to shift the counter to 0, which will change our a. So your a is not 3. This value is a only when this value is 0. That's what we learned in Calc 2. So our job is to take this 2 and shift it into a 0. Now, currently what you have is n equals to 2. Now, how do you shift it to 0? Well, common sense, subtract 2 on both sides. Once you do that, right, you will get summation of n minus 2 equals to 0, going to infinity, 3, 1 over 4 to the n. Now, you will be subtracting 2 for our problems, which are on Wednesday, for the second derivative, because the first derivative will shift the counter by 1. So your original function is starting at 0, your derivative will start at 1, and your second derivative will start at 2, your third derivative will start at 3, your seventh derivative will start at 7, right? So for each term, you will have to make sure that they start at 0, so there will be separate shifting for second derivative, separate shifting for the first derivative, and then the function will be at its whatever base is. All right, cool. So now I'm going to define a new variable. You can say m equals to 0, and you see that you have the counter now that m is equal to n minus 2. So if that is that, then from there n is m plus 2, and that goes up there, because if I am switching the counter on the bottom to be m equals 0 to infinity, then I have to have my n changed to m plus 2, because I have to have everything in terms of m. Hashtag u sub in calculus, right? You have to change all of your x's to u's and dx into du in order to do the u sub. Over here, if you are switching this n into an m, then you have to switch the other one, or you have to switch all of them, right? We'll see. For power series, it's going to be cm plus 2, and it's going to be to the x to m plus 2, right? So all of them switch. Now, we have to peel off these, because remember what the second rule said. The first rule was make this into a 0. We did it. And now the second one is that all of these have to have the same power. Well, I need to go down to m only, which means that I have to peel off 2 of these to have this stay. This is still m equals 2, right? And this is where you finally see that you are getting 3 over 16 and then 1 over 4 to the m. And see, your a is not 3. Your a is 3 over 16 when you have a correct starting point for geometric series, which is 0. So that's what I was talking about. Now you can calculate the sum as a over 1 minus r, which is 3 over 16 divided by 1 minus 1 over 4, right? Multiply top and bottom by 16 everywhere. You get 3 over 16 minus 4 is 3 over 12. So the whole thing adds to 1/4 if I can calculate properly. So what I did is I multiplied top and bottom by 16 over here to kill the double fraction, right? So 16 and 16 cancel, just leave a 3. 16 times 1 is 16, and then 4 and 16 cancel to 4. So that's a 12, 3 over 12, 1/4. All right. Now, one step that as a student bothered me for about a day was when my professor said, oh, well, once you do this and once you have this, then you just write it as a summation n goes to 0 to just change m's to n back. Right, that bothered me a little bit because I said, didn't we just define that m was n minus 2 and not m equals to n? And I was really bothered by that because you shouldn't have double standards in mathematics. But he said it doesn't matter which letter you use, because remember, this is equal to n equals to 2 infinity 3 over 4 to the n, x to the n. So yes, they are actually giving you the same numbers if you compute. So you can actually just rename that m back to n's once you did the conversion, because now you have a completely new a, right? Completely new a. And if you are to use zeros, it will be spitting out the same, right? Because this one you will start, the first term will be calculated when n is equal to 0, right? And it will give you what? It will give you 3 over 16 times 1/4. That's what it's give you, because, sorry, n is 0. It's just 3 over 16. 3 over 16, nothing else. Because n is 0, the whole thing over here turns to 1. When n is equal to 2 over here, wait, why did I write x to the n over here? What did I do? It's just 3 over, yeah, 3 over that. There is no x to the n there. I don't know why I wrote that. It's just the original problem that we started with, this one. I'm not sure why I wrote that x to the n there. I got excited. So if you take a look here, the first number you are computing is n equals to 2, and that's just 3 over 16. Right? So they're the same. So you are allowed just to rename that m back to n once you are done with the shifting the counter, because they have different numbers in their inside of this discrete function. Cool. So now we know that shifting the counter helps us shift the function. Okay. So what are the derivatives? Because isn't this differential equations, right? We want to know, we learned about functions in Calc 2. Differential equations, we want to learn about derivatives. All right, so derivatives of power series. And for vast majority of you, this will be completely new grounds. What do I have? I have my definition for f of x, which was what? Power series Cn x to the n starting at 0 going to infinity, which was C0 plus C1x plus C2x squared plus C3x cubed plus ... So that was your, right, that was your life. What is the derivative? Well, these are numbers. These are numbers. I'm just going to copy those numbers, right? Now, I'm not going to put anything here. I'm just going to say Cn n x to the n minus 1. Do we all agree that the derivative of x to the n is n x to the n minus 1? We better agree on that. That's the first formula you learned for derivatives in Calculus 1. And you have been taking derivative of x to the 7 to be 7x to the 6 for 2 years now, right? So I don't want to hear any discussions in that area. This is a coefficient number. That's a constant. Just copy it down, right? If you have to take 9x to the 7 derivative, you copy the 9. That's technically copying the constant. And then you have times 7x to the 6. I haven't done anything new here, right? Nothing new. All right, so now what's happening with the rest? Remember, I still haven't put anything in here. What is happening for the rest of this stuff? Well, let's ignore that anything here exists for now. Let's just take the derivatives, because we know how to take the derivative of a polynomial. Let's not invent anything new. C0 is going to be 0. Then I have C1 plus C2 times 2x plus C3 3x squared plus ... So now when I reveal what I deleted, where does my sum starts? Where does it start? With what value? Clearly starting with 1. The word clearly is necessary there, right? So as soon as you take the derivative of your power series, your counter must start at 1 because the polynomial works that way. Now let's take a derivative of sine and get cosine. I mean, with power series, you can't get anything else. So I'm going to box this. And let's just practice it on a basic example where I want to take the derivative of sine x and get cosine x. Okay. So the derivative of sine x would be the derivative of the power series 0 to infinity of -1 to the n x to the 2n plus 1 over 2n plus 1 factorial. So I'm taking the derivative of the power series. And before you freak out, just write down the terms. All right? There's no reason to panic or to be, going crazy. This is 1 minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial. Just keep cranking these negative powers, right? And if you want 70 terms, just go, right? Write 70 terms. Make sure you only use odd numbers. Now, you have a polynomial. Start taking the derivative. What is the derivative of 1? Is 0. Fine. What is the derivative of this piece? Right? What is the derivative of this piece? Oh, wait. This is supposed to be an x here. X to the 1. Oh my god. I'm having a terrible day. This is supposed to be x over 1 factorial, so it's just x. Holy nightmare. I am losing it. I'm trying to figure out why I'm so... Oh, yes. If you haven't seen the terrible news, look at the college email. I know there was something that ticked me off this morning. So when I wake up, you know that I have to look at the phone to see which day it is, because I haven't been to campus for 2 months now, right? So my Sunday is the same as Wednesdays, right? So I literally every morning, the first thing I do is I look at the cell phone to see what day it is. Is it a Wednesday? Is it a Saturday? I have no clue. And then I read the emails to see if we are coming back to campus. Well, there was a completely opposite email this morning, and now summer 2 is online completely as well. So there you go. Go and be pissed for the rest of the day as well as I am. So now that I ruined your day as well, let's go and take these derivatives. Yeah, so it's kind of hard to focus on these things when you... Anyway, so what's the derivative of x? Is 1. Yeah, yep. It's online, so more of this nonsense. Anyway, so we have x, derivative is 1. What is the derivative of... Oops, there minus. The derivative of x cubed is 3x squared. And then what is your factorial? Your factorial is 3 times 2 times 1, right? Plus 5x to the 4 over 5 times... I'm just going to write it 4 factorial, because that 4 factorial is going to have 4 times 3 times 2 times 1. I just want to write all of those things. Minus 7x to the 6 when you take... Right? And this is 7 times 6 factorial plus 9x to the 8 over 9 times 8 factorial minus ... Now I'm going to cancel all of these puppies, and you end up with what? 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. Hey, that's all evens, right? And if I have all even ones, that compresses into... See, your answer when you solve this mess of power series in 8.2, your answer is going to look something like this. And then you condense that into negative 1 to the n, 2n, x to the 2n divided by 2n factorial, which is a cosine x. Right? And that is it. So this is what our life is. Now, some of you that been paying attention probably, and I'm just waiting for that question to pop up because I'm bound to have someone ask, hold on, Professor Nick, didn't you say that anytime we take the derivative we will start with 1 and not with 0? Yeah, I did say that. So this was me cheating, right? Because I know what the answer is supposed to be, right? That's me cheating. How about I write my formula starting at 1, because the derivative should start at 1 if the problem started at 0, original function. And then we'll see that by shifting the counter by 1, we actually will get this. So I cheated. I cheated because I know this series. I memorized it, right? I memorized it. I said that's one of our basic ones from the beginning of the lecture, which I said these are the ones you should have memorized. There it is, right? And it does start at 0. So I cheated, right? I cheated because I knew, first off, I knew that the derivative of sine is cosine, so I know what's my target answer. And the second thing where I cheated is once I got the series, I just wrote the cosine one because, you know, I knew all of that. But let's say that you actually have never learned power series, right? Let's say you never did this before and you are figuring it out for the first time. You would be following what Professor Nick said right in that definition up there. When you take the derivative, right, your power series, when you condense it, will be starting at 1, going to this, right? All right, so let's go. What do I see here? I see some power alternation here, the sign alternation. So I'll have -1 to some power, right? And let's put that power to be now n plus 1 here, right? I can do n plus 1. I can do also n minus 1. Or I can do n plus 3. The goal is to have the even number here on the first term, because -1 to the even will give me the positive value. So whether we're going to put +1, -1, +3, +17, right? I don't care. We just need n plus 1 there. Now, all of this is going to be, well, this is a 0 factorial here, right? That's a 0 factorial. So if I'm starting with 1, this to me looks like a 2n, right? But it's going to be shifted by 1. So this is a 2n, but it's shifted by 1 value. So it's actually 2n minus 1, so it's 2n minus 2 factorial. If you didn't follow this, well, let's see what happens when I plug in 1. What happens when I plug in 1? When I plug in 1, 2 times 1 is 2, 2 minus 2 is 0, I get my 0 factorial. When this switches to 2, 2 times 2 is 4, minus 2 is 2, 2 factorial. When this switches to 3, 3 times 2 is 6, minus 2 is 4 factorial, right? So I have that. So now the denominator works. And as we know it, the power over here has to match the denominator. There we go. So this is actually what you should get, right? If you follow the differentiation rule, you get this mess. Now you say, oh, that's a minus, so let's use n minus 1 here. Right, use n minus 1. Then you say, okay, I got this mess. Now, I know that we also should know how to shift the counter, because if I'm shifting the counter back to 0, then I will be able to combine original function with the derivative. Remember what the goal is. The goal is to have a y and a y prime and a y double prime and y triple prime, right? All of them in the same equation. So if I'm going to add all of those power series using those blue properties, if I'm going to add all of them, then I must have them all start at 0, right? So I did the derivative for this thing, and now I need to shift my counter to 0. Now, how do I shift my counter to 0? Well, this is n equals 1. We subtract 1 on both sides. That will create m equal to 0 here. And we still have our things in here, but hold on first. I have that n minus 1 is equal to 0, which is m equals to 0, which tells me over here that m is equal to n minus 1, which tells me that anytime I see n minus 1, I should put m for it. That also tells me that 2m is 2n is 2n minus 2. I just multiply the whole thing by 2, right? So now I know what to replace. It's a basic substitution, and we're doing it on. We're not doing any integrals or anything like that. This substitution is qualified as basic algebra, right? So you just have to make sure that you are subtracting the appropriate value to make a 0. Obviously, for the third derivative, that will be a 3, so you're subtracting 3 on both sides. For the second derivative, you're subtracting 2, and so on. Anyway, so now I have this division line here, and what do I get? I get negative 1, and my n minus 1 is changed with m. And my x, what is the n minus 2? It's just 2m. And what is n minus 2? It is 2m factorial. And yay! That's a cosine x, right? Just change them back to m's. So all of these definitions work, right? And depending on your knowledge of chapter 11 from Calc 2, this will be, a chapter that you will deal with easily, or this will be a living hell, right? It would be very advisable to go back to chapter 11 from your Calc 1 class. I will be teaching tomorrow sections on this in Calc 2. So if you have time, tomorrow 6 p.m., Tuesday 6 p.m. If you have time, tune in again. And I will be teaching my Calculus 2 class. I'll be teaching properties of power series, and we'll do derivatives and integration and so on. It will be a good refresher. And then Wednesday, 11 a.m., right, given that the YouTube doesn't give me the headache it gave me today, well, now I know what the issue was. They switched my stream key without telling me. So everything was streaming, but it was not going through. It was not linking to my account. Whatever. It's the issue. It's a streamer's issue. So, but I figured it out, and we're back playing. All right, cool. So now you have the definition for a function in terms of power series. You have the definition for the derivative, and you also know that your counter shifts here. So on Wednesday, when we actually do differential equations with this mess, we will be shifting this back. Remember that this is a constant. What's happening with your second derivative? That dies. Where does your second derivative counter start? At 2. Right? So, as you go on, you can deal with any derivative now of any order, because you know that your counter has to shift, and you will be there. All right, cool. I'm not sure why was this necessary to say, but I guess it is necessary to say that I don't know if I'll put a Reddit theorem. two power series are the same if an equals bn. So we have summation 0 to infinity an x to the n equals summation 0 to infinity bn x to the n. I'm really not sure why this needs to be stated, but yeah. The question on the chat says, would you want to shift the counter to go straight into the shortcut? Because we know, if you know the shortcut, you are using the shortcut. There is no reason to write the full page of calculations. Obviously, you will be submitting your work for partial credit, right? So I will look at it. Now, if you already know that the derivative of sine is cosine, you will just be using that. But the trick is that this is not designed for the basic sine and cosine functions. This is designed for the composite functions and nasty differential equations that you can't really, because the idea here is to, you know, use a couple of terms, maybe 4 and 5 terms, and then deal with this in the terms of polynomials rather than going through the whole hell of you know, infinitely many terms and you know, when differential equations is not possible to be solved in any other way. So the answer to that question is yes. If there is a shortcut that you see, you can always take the shortcut. So there we go. The second question was self-answered in the chat, and I'm just gonna support that, say yes. Yes, yes, yes. Okay. Now, the part of this lecture is also radius of convergence from Calc 2. This is exactly what I will be teaching tomorrow. And this is more of a theoretical part. We actually don't need this piece to solve differential equations. This is more theoretical to tell you that the power series will converge on the functions so that you can convert your differential equations into power series, and then those power series converge to the functions that were there originally. Again, it's a theoretical piece, and it is just for us there to know that we can actually use this, right? And the convergence of the power series, we use the ratio test. Those of you who want to review those details and care, other than teaching derivatives, integrals of power series and basic properties and composition of functions within power series tomorrow at 6, this will be also the part of that lecture. So tune in tomorrow at 6 p.m. Tuesday, and I will, you know, go through the convergence. We don't need it. I mean, we're not going to use it in differential equations in any of your calculations, whether it's homework or exams. Now, the last thing that I want to do here, which is the last thing they talk about in the section, is to actually convert the first order differential equation into power series. We're not going to do anything with it. We're just going to do the conversion, right, along with shifting the counter, just to make sure that we all understand how to convert that mess. And then solving these things we're going to deal with in 8.2. So convert, and now we can put any, the book did a couple of these examples. I'm just going to jump into the homework and see problem number 6. X minus 2 times y prime plus y equal to 0. To PS, convert to power series. All right, so this is our step 1 of every power series differential equation problem. You have the differential equation, you need to convert it to power series, then 8.2 kicks in to solve it, and to go back into solution, again 8.2, right? There is the rest of chapter 8 as well, which unfortunately we don't have time for. I think the syllabus is asking us to go through 8.3, but we only have 2 classes left. There will be a review on Friday, and final exam Saturday to Tuesday, or Sunday to Tuesday, final exam or exam 4, whatever you pick, one or the other. And then some of you said, can we do both? Of course you can do both, right? You can always do more work, right? So if you are choosing to take exam 4, then the average of your exams will be calculated as 30% of your grade. And if you take the final, then the final is calculated as the final exam. Anyway, all right, let's convert this. So what do I have? Well, we know that the power series is given as Cn x to the n. And we should also know that the derivative is given as Cn n x to the n minus 1 from 1 to infinity. So, memorize it. This one is the basic definition for power series of a function. Whether I write y or f of x, who cares? And then over here, this is your basic derivative. See, that's your derivative of x to the n. This is you copying the constant, and remember the counter shifted. So memorize that. That's your basic definition for derivatives. All right, cool. So time to plug everything in and see what we got. X minus 2 times the power series 1 to Cn times n x to the n minus 1 plus the power series 0 to infinity Cn x to the n equal to 0. Next time someone mentions the weather, how beautiful it is to make a small talk, this is your response to it. Immediately shift it to power series. All right? If you have something to write, start writing it out. Now, this guy here distributes into power series, and I'm getting 2 separate power series. I'm getting a power series x summation Cn n x n minus 1. And you don't have to write the infinity on top, but you absolutely must write this every time. Otherwise, you are going to lose it. Now I have minus 2 times the power series infinity 1 Cn n xn minus 1 plus power series 0 infinity Cn x to the n equal to 0. So welcome to the differential equation with power series. And what was this? There was the first order, one of the simplest examples? Yes, yes, yes. So what now? Well, now you look at this mess and you say, all of my counters must be 0, all of my powers must be n. Use whatever witchcraft you can to make that happen. Now, it has to be valid mathematical witchcraft. You can't just say, oh, let me just, So this is what we have in terms of our problems. So let's go and deal with this. So I go with shifting the counter. Now, I need to shift these guys to 0 and see where is that going to take me. But hold on a second. This multiplies in. Before I shift anything, this x jumps in there and does what? When this one jumps in, it creates Cn n x to the n 1 to infinity, and then the rest of the series stays the same. So do we see what happened there? That one now lines up. The counter doesn't line up, but that one lines up with this. And the counter is off. And over here the counter matches, but the power doesn't. All right. So what now? All right. So the best practice here is to first, because you can't combine these until all of your powers are the same and all of your counters are the same. But you start with fixing the counters, and there is one more trick up our sleeve which can help you greatly in this, and that is peeling off terms. Right? So I can match this and this term in one shot instantly by peeling off a term from here. What do I mean peeling off a term? You see, this one starts at 0, and then next one is 1, and then 2, and then 3, right? So if I compute this for n equals to 0 and leave the rest in the sum, then that sum will start with 1. And then I will match the 1 and the exponent at the same time by using that very basic trick. So now, what I'm going to do here is I'm going to peel 0, which will give me c0x to the 0, plus the summation 1 to infinity cn x to the n. That's what happened, right? And now c to the 0 is, x to the 0 is 1. So, summation 1 cn n x to the n minus 2 summation 1 to infinity cn n x to the n minus 1, and then I have plus c0 plus summation 1 to infinity cn x to the n equals 0. If you take a look at these two series, they can be already put together into a single series. They start with the same number, and they both have the same power. It doesn't have to be 0, right? The example we did with geometric series requires a 0 so you can calculate the sum. That's a theorem. But for the power series for differential equation, if each one of these numbers is 28, fine, right? Your job is to put them all to the same start and the same exponent. We don't care what is the starting number. So I am able now to combine these two power series into a single power series. I'll put C0 term first, right? I have 4 separate terms in there, right? There's a minus, then a plus, and a plus, so 4 separate terms. I'll put C0 first. Then I'm going to combine these two into a single one. What I have here is Cn times n plus Cn and then x to the n. I hope we all see that when I put these things together using that blue rule, right? And I factor out Cn, what I have is Cn. And then Cn times n, that's the first one. You can write NCn. I mean, it's nicer. Cool. And then I still have minus 2 summation 1 to infinity Cn xn minus 1 equal to 0. So now what is left is to combine these two together, and now we are going to have to do some shifting the counter and some other magic because, see, the powers don't match. So when I shift the counter to match the powers, the counters on the bottom are going to shift as well, right? So the first order of business is to take the 2 inside, because I can't operate when this 2 is in here. Minus is okay, sorry, the 2 is the problem. So we're going to kick that one inside. So NCN plus Cn x to the n minus the summation 1 to infinity 2Cn xn minus 1 equal to 0. Now, we don't like n minus 1 over here. That's a problem. And we can start by saying that n minus 1 is m, right? So whatever we don't like, this is n equals 1, n equals 1. So if I subtract 1 over here to make these zeros, again, it's not necessary in every problem, but if I do that, it will line up nicely that n minus 1 is m, which is m right here. So I have C0 plus summation m equals 0 to infinity, and now every n becomes m plus 1. So I have m plus 1, cm plus 1 plus cm plus 1 times x to the m plus 1 minus summation of 2cm plus 1 x to the m equals 0. And we have no more n's. We have our counters are matching, and all I need to do is to peel one x off, and I will be able to combine the series. Now, when I write this one as x to the m times x, right, then this x can go out, and then we should be able to combine the series. So C0 plus summation m goes from 0 to infinity. And what do I have here now? I have, maybe I should use the big ones. There we go. I have m plus 1, cm plus 1, plus cm plus 1, all of that times x, minus 2 cm plus 1 times x to the m equals 0. I think we combined it all. So let's see. This is the coefficient times x, the x to the m kicked outside, minus from the other series, we have 2cm plus 1. Yep. Shouldn't it be 2cn n x n minus 1? I did use that. That was all the way on the front, right? On the beginning of the... The tablet is overheating now. It's starting. I should go get the ice pack. This is where we used it. And that goes here. Because that's the derivative. I'm not sure what you are... where you're pointing to. So the function goes there, the derivative goes there, so they're crossed, right, for our application. And then you just follow calculations. Split the sum, because you have to distribute x minus 2. You split the sum and you keep combining what you can. Now you can rename everything. 3 lines up from the bottom, it seems like n just disappeared. 3 lines up. Are you talking about this step here? The one above it. So for the one above, for this one, I combined the purple terms together, and this term is that term. Oh, I dropped the n. Now I see, yes. Okay, I just didn't write, yes, there is an n xn minus 1. When I was copying this, I missed to write an n in here. So there is an n x to the n minus 1. Okay, so it was a copy mistake. Now obviously that's a big deal because that sets everything off. There has to be over here an m plus 1. Obviously that would give us a wrong answer. And then that will travel here as m plus 1. Good eye, good eye. Yep. Excellent. Good. Now, what's the goal for the next class? The goal for the next class is to learn what to do with this. Yeah. So, this is it for power series. We have conquered the beast, right? Reviewed Calc 2. Did one of the conversion problems. They did an easier example, obviously, in the book. Converting something like this, like y prime plus 2y equals 0, or something like that. We had the term with x, which creates this mess here. So you have an easy example to read in the book. You have this spicier, way spicier example that we did here. Please practice those. Tune tomorrow at 6 if you need to brush up on power series, especially those function compositions, and those interested in reviewing the radius of convergence, even though we actually don't need it for the course, but it's still a part of the course. I have to go now. My algebra class starts in 1 minute, so I have to go and deal with that. Your exam ends tomorrow, and email me your... Oh, there you go. Okay, when we send the work for the exam, email either Canvas or regular email anytime, right? You can take the pictures. Some of you are sending me the screenshots, whatever form. Send me the work in the email for exam. And then Wednesday we have a class, Friday we have the review, and the next weekend, Sunday through Tuesday, will be the final. One more time, I'm not sure if that was a troll question or not. The exam is open till noon, not midnight. Final will be open at midnight because the date. All of the other exams are closing at noon. So tomorrow noon, you better start tomorrow at 10, right? Better start at 10 if you want to have enough time to go. 10 a.m. 10 a.m. And the exam will close at noon, 11:59 a.m. All right. See you all. Gotta go do algebra. Bye.